Okay, so I wrote a summary of what we discussed yesterday. Just to remind ourselves, there was this 4x4 Hamiltonian that we all know how to diagonalize by now. It has all phases from a vial semimetal to an insulator to a Dirac semimetal. It can be written in some compact way with some matrices that you can read from here. We wrote it also as an action with some term that we identified that broke what we call particle Lorentz invariance. And we added here a matrix that allows us to incorporate the Fermi velocities. And the spectrum, we found it was gapless or gap depending on the size of B squared and M squared. So basically when the mass dominates, then everything gaps out. When this Lorentz breaking term dominates, we have a semimetal. And then we can move the vial nodes in momentum with the spatial part of B, or in energy with the temporal part. And so we wrote it as a 4-vector. Remember that B squared is this thing. And the spatial part broke time reversal. The temporal part broke inversion. And so, so we're going to leave this part here for a while. And now I'm going to try to connect this with models that people have been using, or discretized models in the lattice. And actually, it's going to connect to something Michael Wimmer talked about yesterday, just models in the lattice. And this has been a recurring topic in high energy physics, how to regularize fermions, how to regularize or construct theories that reduce to, you have a low energy theory and you want to you put it in a computer, how you discretize it. And there are many ways of latticizing or discretizing this theories. So I'm going to call it discretize. I'm going to talk about 3, but there are many more. So I'm going to talk about one that I'm just going to call Lattice Fermions, because nobody uses this one, and so it doesn't really have a name, but it's useful to illustrate why it doesn't work and why we need others. But it's the most naive thing one can do. I'm going to talk a bit about Wilson fermions that are very important for us in condensed matter. And I'm going to talk about inspired Wilson fermions. So this third is just some example of the things you can do, and I don't think there's a realization of this in condensed matter, but it would be cool to find one, I guess. Or if there is, maybe somebody knows, but I don't. Okay, so just to throw some names in case you encounter them, there are also staggered fermions, twisted mass fermions, many fermions. But I guess these ones are pedagogical in some ways. Okay, so let's start with lattice fermions. So for that, I'm going to use just for this part, I'm just going to set all b's to 0. So I'm just going to go, spatial part of and temporal part just to 0. And so I'm going to use the Dirac Hamiltonian. And now, if you have a linear dispersion and you want this to happen at low energies, the easiest map you can define is, so I'm here one, is to take your ith component of momentum and change it for a sign. And the mass, let's say we don't really think this is going to cause any problem, so we just call it big M just to change its name, but it's really the same object. because you know, so let's say I want to put this theory in a computer, and I want to discretize K, and or I'm a condensed matter physicist, and I know that I have a lattice, and I want to recover something that at low energies, meaning when K is small, or where I expand K around some point, I recover a linear theory like this one. So I can do this, and immediately you realize that, well, if I expand, you know, I get a Hamiltonian that would look like, well, simply, let's say sine Ki sigma I m, m sine Ki sigma I, something like this, right? Sum over I. Now, if I expand around gamma, then I'll get kx times sigma x, ky times sigma y, kz times sigma z. And I'll get back to this guy, right? However, you already see the problem, that if I expand around 0 pi pi, or pi pi pi, or pi 0 pi, all the corners of the Brillouin zone will have this Hamiltonian with some signs changed. And, you know, some depending on where I expand this, the sign will have, either it would be 1, or it would be k, or it would be minus k. So this is a problem that is known in high energy as the fermion doubling problem, meaning that when I put my theory on a lattice, the lattice is periodic, so I have other points where I recover copies of this Hamiltonian. And in fact, I recovered copies of this guy already. Like if I just, you know, imagine I just have a 2 by 2 Hamiltonian and I try to do the same trick, then I would see that I can never have, actually this is a minus, sorry. I can never have one single chiral fermion. There will always be, at the corners of the Brillouin zone, there will always be what they call doublers. And this is a fact that can be proven rigorously mathematically. So meaning, you know, if you diagonalize this Hamiltonian, whoops, if you have a mass, you would see something like this. So, whoops, I guess something like this. And if it's massless, you would find something like this. So you would find like not only at, so this is K, this is E, this is K, this is E. So not only at gamma, I would have gapless degrees of freedom, but I would also have at, you know, let's say pi 0, 0. Okay, so we have to do something about it because, well, we would like to, you know, if we want to ask, so if we ask that we recover a theory like this in the low energy, we're having a problem because we're having 2 to the d copies of this theory, where d is the space dimension. So in fact, what Nielsen and Niami proved, this is theorem, is that under assumptions of unitarity, locality, and translational invariance, I will always have doublers unless I break chiral symmetry. Okay? So always pairs of, you know, let's say vials at low energies unless okay. Yeah. How do you get that? You just diagonalize this Hamiltonian with m equals 0. So this is m, sorry, yeah. Thanks. So this is m equals 0, this is m not equal to 0. You know, you remember that when m was 0, here we had a chiral symmetry, right? What we're saying is that, you know, unless we break that chiral symmetry, we cannot get rid of these copies. And I'll explain how you do that, because that's exactly what these fermions do. They break chiral symmetry to get rid of the doublers. What is the?
Which object is unitary local?
Oh, the theory, I guess. Yeah, just Lagrangian, I guess. Yeah, yeah. Yeah, actually, I'll write a kind of non-local. So now, basically, now what I'm going to do is, so Wilson fermions evade or write some other version of this lattice theory by breaking chiral symmetry, and we see how that happens. So chiral symmetry would be broken. And these guys kind of break chiral symmetry in an interesting way, and also, depending on how you define it, can break actually locality. So that's what I'm going to do next. So is this clear? We just, you know, try to put this on the lattice, and we encounter this doubling problem. So now we're going to try to find some other route by sacrificing chiral symmetry. So that's number 2, Wilson fermions. So in this case, the map is similar. So ki goes to sine of ki. You know, remember I is like x, y, z. But now, what I'm going to do is m, instead of writing just a single, just a mass, I'll write it as sine squared ki over 2, which, you know, you can also write as 1/2 sum 1 minus cosine ki. Okay, so this is a sum that goes over x, y, and z of the sine squared ky over 2. That you can also write just using trigonometric identities as this guy. And the reason I write both is because high energy books usually use this, and we in condensed matter usually use this, but they're the same thing. And the reason you do this is that now, well, you see what this does. This term here will add a mass at the corners of the Briand zone, even when m is 0. So when I take the limit m to 0, the corners of the Briand zone would be gapped due to this term. So the dispersion now look something like, you know, with generically it would look something like this, but I can fine tune it. I mean, so this, you know, you apply this to the Hamiltonian I had before, which was this. So you apply this map to the Hamiltonian that's down there. You diagonalize it, and you find that, you know, you can find a dispersion that goes like this. But here you're sacrificing chiral symmetry because, you know, even though this parameter is 0, this is not, and so I cannot define this gamma 5 that we defined yesterday. That define chiral symmetry. So so this is no longer true for. Sorry, this is true, but it's not longer true that I can, for m equals 0, I can commute that matrix and say that that's a symmetry because of this term. So those are called Wilson fermions. And in fact, you already saw a Wilson fermion yesterday in Michel's talk, and actually I think in other talks that I forget which, but probably Titus's. Because the Hamiltonian for a Chern oscillator that Ivo described is essentially, so now I go to 2 plus 1 dimensions. So now this is a sum over, let me write it explicitly so that's no confusion. Ky sigma I m minus cosine kx minus cosine kz sigma z. So this Hamiltonian is defined in 2 coordinates. Sorry, this is y. 2 coordinates in momentum space, so it's a 2 plus 1, so 2 space dimensions, one temporal component. And this is the 2D version of the Wilson fermion. So if you compute the Hall conductivity of this guy, depending on the mass parameter, you would see that you can be in a phase where you have Chern number 1 or a phase where you have Chern number 0. So a Chern oscillator is nothing but a Wilson fermion, actually. And this is, if you remember from yesterday in Michel's lecture, he defined 1/2 of he said the 1/2 of the BHZ model that described 1/2 of the spin Hall insulator. This is exactly it. Now if I go to 3D, let's see, let me erase this. If I go to 3D, so we're talking about this part of the Hamiltonian. Okay, so now I'm going to apply what I just said, and I'm going to get, sine ki gamma I. So this is h. I'm not going to give it a name, so sine ki gamma I plus m minus sum over cosine ki gamma 0. So I'm just applying this thing here. And actually this Hamiltonian describes a topological insulator, a 3D topological insulator. So this is sum over x, y, z, sum over x, y, z. And this, you can convince yourself that, if you change the sign of the mass, you can expand, for example, you can expand this Hamiltonian close to the gamma point, and what you would get is, k dot gamma plus m minus 2, 3, right? Close to the gamma. So this, this would be my m here. And so if you start playing around with the sign of this mass, you can define a phase that has a positive gap, let's say, or a phase that has they would look the same, but you can define something that has a plus gap, m, say bigger than 3. Of course, there's some scale that I'm setting to 1, but bigger than 3t or m less than 3t. And the boundary between these two guys, so if I let m vary in space, the boundary between these two guys would have a 2D gapless Dirac fermion, and so that's a topological insulator. So this Hamiltonian actually can describe topological insulators. So you see that Wilson fermions are essentially the way one can construct topological phases very easily. So one can, in principle, do the same for the whole Hamiltonian, because, well, these things don't depend on momentum, so they stay the same with this map. And that will, have a very rich phase diagram where you can find, you can put this in Mathematica with this or in Quant, let's say, and you get this map, apply it to this Hamiltonian with the B0 and Bi, and you start playing with the parameters, and you see that you can find phases that look like a topological insulator, a weak topological insulator, Weil semimetal, a Dirac semimetal. So you can get all types of phases just by doing this simple map. So this is a pretty powerful tool. Yeah. Yeah, Fermions in the lattice. I guess that's how they formulate it, yeah.
So here, which of the two conditions did you break? Did you broke down?
Well, I broke, it looks like I can fine tune to have just a single Dirac. But here, Nielsen-Ninomiya doesn't apply because I'm breaking chiral symmetry. So they're just saying that under these assumptions, you will always have pairs of vials unless you break chiral symmetry. So by adding this guy here, I guess what they refer to chiral symmetry is, setting this M to 0. Before we didn't have this term, we set this M to 0, and we had like a block diagonal Hamiltonian, but then we had a lot of doublers. But now we set this M to 0, we have this guy here, a Dirac fermion. And all the doublers are gapped. But this gap precisely breaks chiral symmetry.
I guess what I'm trying to understand is it not possible to write the Fourier transform of that Hamiltonian in real space as a localized Slovenian representative or something like that kind of thing?
Well, depends on the values of the parameters, actually, because if you crank up M to infinity, it becomes larger than any other energy scale, and it's kind of like a local potential. Like if I write this in real space, it would be just a square lattice in a way. I can write it as a square lattice, and this M is an on-site potential. So if I crank it up to infinity, then I can write it as a localized. So it's trivial. It's a trivial phase. But now if I close the gap and open it up again, then I go into the topological regime and I cannot write it like that anymore. I think, yeah. I guess in 2D is maybe even more obvious. Yeah.
Some of these models we're dealing now with like the ability to connect them to a real material problem, then you have the same properties, right?
Yeah. I mean, usually, well, I guess that's the art, I would say. Yeah, I mean, you can start promoting things. Like, for example, here I chose the same hopping for each k. So, but you can in principle have different coefficients here, same as here. You can have anisotropy. So you can try to model some particular or like fit, let's say, some particular band structure with allowing these parameters to vary, and if you're interested in a particular material in a particular part of the low energy, you would know that, as we learned from Andre, you would know like what symmetries. So you would first look at the symmetries, then say, okay, well, I want to describe my the low energy excitations close to the gamma point, and so these are the terms that are allowed in my Hamiltonian, and so you put them all with all in principle different coefficients and start playing. Yeah, but I mean, if you see like if we go to the supplementary material of all this like Weil, the real materials like TAS or so on, you would see that essentially they're kind of generalized versions of this Wilson fermions, essentially. I mean, yeah, of this Hamiltonian. But yeah, depending on what you want to describe, you would do one thing or another. Okay, so if there are no more questions about Wilson fermions, I'll go to describe the third type, which is kind of more exotic. And I'm not going to go into too much detail because it's never used, but I don't know, maybe someone here knows how to realize it. So it's worth describing. Also, it illustrates how other things can be done beyond Wilson fermions. So Ginsberg-Wilson. So what this guys did was what these guys did was, okay, let me so remember that our chiral transformation from the other day was something like this. So what they want to do is they want to promote this transformation to be the following thing. So A is the lattice constant, which I implicitly assume 1 in the other examples, but let's leave it here, find it. So the continuum limit would be to take the lattice constant to 0. So this guy would disappear, and I would recover the same chiral transformation. So what one could expect from this generalization is that chiral symmetry is broken, but only to first order in the lattice constant. So lattice corrections would break chiral symmetry, but only at order A. So what they do is, so I haven't defined this D, but it's some sort of operator, and I actually will never define it because it's quite a complicated one. But if you want to know the action in general, or what this D really does, so let X and Y be 4 coordinates, so I include time and space, but there are 2 of them, so that's why it's non-local. So D sits where usually the gamma mu, k mu, or gamma mu partial mu kind of sat before. And so one can show that, or one can ask whether there's an operator D that satisfies such that, so this is gamma 5D, A lattice constant D, gamma 5D. The way you have to read this last term is actually, I'm going to write it explicitly because if not, it might be confusing, is, say, X, Z, gamma 5, D, Z, Y. So you see, what this guy did was, let me replace this gamma mu by D, and ask whether I can define this D to anti-commute up to order A with gamma 5. So if I take A to 0, this guy disappears, and I recover this type of commutation relation, and I can define a chiral symmetry. And now the question is what this D is, and the D is just a solution to this equation. And in fact, Ginsberg and Wilson they proposed this in, I think, 82 or early 80s, but it took more than 10 years for somebody to actually give an expression for this guy. So I'm not gonna say what is that, but the most popular version of D, or one solution, let's say, let me call it, it's called an overlap fermion. So it's a solution that, okay, before I say that, as you see, I kind of broke locality in a way, and I also broke chiral symmetry, but only at order A in the lattice constant. So that's how I evade Nielsen and Nemiya. But I have to give a form for D, and in fact D can be local because, as I say, I'm still breaking chiral symmetry. And a guy named Neuberger gave an operator D that's local. So it actually only depends on one of these coordinates. So it's a delta function, or a Kronecker function. That it's local, but still, you can write a finite. It's a matrix, and satisfies this equation. So, and those are called overlap fermions, or he called them overlap fermions for reasons that I'm not going to discuss. But just so you know that there's a solution to this equation that's local and that you can write it in some way. So as far as I know, overlap fermions don't really exist in condensed matter. I'm not sure if there's a fundamental reason or not, but you can dig into it. And yeah, so this Ginsburg-Wilson fermions are nice because they recover kind of nice properties when A go to 0, but they have sort of corrections. So you can define anomalies, you can define things like that, and they would be modified by terms that are order 1 in the lattice constant. Okay, so this is all I have to say about lattice fermions. So now it's a good point to take questions, if there are. If not, we will go to the responses of these theories to external electromagnetic fields. Yeah.
So I guess the idea to do lattice stuff here is to be able to compute things numerically, right?
Well, yeah. I guess for them, but for us, we always come from the lattice in a way. So. Yeah, yeah.
But this is within hearing that how there is a lot of physics just dictated by symmetries and so on, and I guess that if you want to do some theory about some system which is some continuous, and then you discretize to do some, let's say, numerics, you change the symmetries of the problem, right? You lower the symmetry, so you put in, to go from one continuous to a square lattice, you break continuous translations, you break rotation, so does it have consequences?
Yeah, I guess, the point of introducing this, especially Wilson fermions, is that it's an easy way to construct topological phases without thinking too much. You get, you start with a low energy theory, or at least, if you like starting from a low energy theory, it's very easy to construct things that you can put on a computer or just simply, make sure that they have topological phases. I guess it's a tool for modeling. Like now, if you want to model real materials, then now you have to think harder and go along the lines that Andre was thinking about, thinking about symmetries and thinking about that. So I guess the point is also that you can ask the question, and this is partially of what I'll do in a second, is that are responses to external, let's say, electromagnetic fields completely determined by this theory? Meaning, usually we think that if you have some low energy excitations and you perturb them with a small electric field, a small magnetic field, then you can find the linear response. And so in principle, this theory would say, okay, compute the linear response with this theory and you would get an answer. But in fact, that's not true. You will see that there are some intrinsic ambiguities in these theories that, since we relaxed Lorentz symmetry, they start to appear, and those will be fixed by some connecting the theory to the lattice in a way. So Okay, so great. So now, exciting part. So this is point 2 of the list that I guess. So yeah, so as I was saying, it looks like if I give you a low energy theory and I ask you what's the conductivity, you should give me a straight answer. You calculate it, go to your many body book or whatever, and you just calculate it and give me an answer. Turns out it's not that simple sometimes. So quantum field theories can be finite but undetermined. So what do I mean by this? So I'm pretty sure you have heard, actually we heard it from Jens the other day, that you heard that sometimes you have to renormalize quantities. What does that mean? You calculate observables, or you calculate, you try to calculate, if you like Fermion diagrams, you calculate Feynman diagrams, or some observable. And you very quickly realize that sometimes the integral you have to do is divergent. And so you have to regularize in some sense. You have to put a cutoff. You have to use some sort of trick to kind of tame or like this divergence. Now then what you do is you say, okay, well, I'm going to hide these divergences in my coupling constants, and these coupling constants are going to run, or these observables are going to run. And that's the beta function that Jens showed. How as I scale some parameters, system size, energy, then this coupling constants or the observables that I compute with them, they run. But this is something different. Here, observables will be finite. So the integrals will look divergent. But when I compute them, there will be no divergence. However, the result will depend on the regularization. Meaning there are many ways of regularizing theories, and each one of them will give a different result. And this is bad because, if we're asked by an experimental, what's the conductivity of this? And you have 3 methods and each one of them give a different answer, what do you say? You go, you leave physics and go surfing. So maybe that's what we'll do today, but but hopefully there's a better way in life. At least we could choose to keep on in physics. And so what I'm going to illustrate this fact with some examples, and I'm going to end up saying that this is one of those theories. Okay, so the example I'm going to use is in 1 + 1 dimensions. And it's very similar to this action, but it's actually the simplest action you can think of. So I'm going to put a 2 here. Gamma mu, k mu, minus e gamma mu, a mu, psi k. Okay, so what is this? So I could define in principle the matrices if you want. So I just have one direction, so I just have one temporal, one spatial, and there's one gamma 5 matrix. And if you go back to the Hamiltonian language, you will find this Hamiltonian is very simple actually. Well, let's say it's just two chiral states. It's already diagonal. I mean, I wrote it already diagonal in the diagonal basis. So it's just two. Well, actually, I draw them separately, but they're in the same point in momentum space. Maybe I should draw them in the same. Oops. So they're just two chiral fermions. One propagating to the left, one propagating to the right. And now I want to ask, what is the response to an electromagnetic field? So I want to calculate the current. So how do you calculate the current? Okay, so I want to calculate the expectation value of the current. So, remember that this mu is 0, 1, 2, 3, so the current is defined as rho, the density, and the vector current. Maybe there's a C or something, but it doesn't really matter. And I want to calculate it at a given momentum. And what you might remember from your field theory, you all said that you were exposed, but if not, I'll remind you that the current operator I can define as functional derivative, of the action with respect to a mu. And this thing is going to depend on a mu because I'm gonna calculate it as a perturbative expansion in this coupling constant or this field, and so it's going to have a term that it's linear in A. It's going to have a term that is quadratic and so on. But I want to calculate linear response. So this is P. This is P. And this thing we call the polarization function. Okay. So how many of you know how to calculate the polarization function? 1, 2. Okay, maybe I should explain how this happens. So, okay, how many of you know what's an effective action? Okay. So the effective action has this thing in it. I'll show it right now. So effective actions. So let's see. So let me write the partition function. It will depend on A because A is an external field. I'm not going to integrate over this A. And as you might remember from your field theory courses, I can write it as a path integral. See over this Grassmannian variables of E I S psi A. So this S psi A is whatever action. In this case, it's going to be this guy. But whatever action I can think of. And the effective action is essentially saying, well, let me suppose I can do this integral, and let me write something that looks like an action, but I already did this integral. So I'm going to define it as this object, and I'm trying to calculate it perturbatively in A. Okay. Now, well, this theory is quadratic in the fields, and this is a Gaussian integral of a quadratic action. So I can write it as a determinant. And in fact, I'm going to write it in the following way. So where do I get this from? So it's the determinant of the, let's say, kernel of this action. That's just Gaussian integration. If you don't understand this step, it's just a mathematical step. It doesn't have any physics. So what is this that I have defined here? This is actually this object. So I'm going to call this this guy here, define it as Green's function to the -1, actually with an I, or minus I. So Green's function to the minus I is just I over gamma mu k mu. This thing here, I just define it as my current, and the A is the A. Okay? So actually, maybe with an E here. So this is just this object. Okay? And now I can write it as this, using the properties of the determinant. 1 minus G0 minus 1 J mu A mu. Okay? So I just pulled out this is the -1. So I just pulled out the G. And this factor I'm not going to really care because you always, well, there's some normalization when I calculate observables. So I always divide by the partition function without fields, and this guy is going to go away, so I don't really care about it. So I have to calculate this object. So how do I do that? I use another identity, which is this guy, which is very important. It's always used. So determinant of a matrix I can write as E trace logarithm of that matrix. Okay? Actually, you can learn all of this in Alex's book, by the way. I guess. So now I can expand, so I can write this determinant using this. So you see E to the trace log of A is determinant of A. So what's A? A is this. So E trace log of A, so this is, trace log of A is exactly the effective action. Okay, so the effective action, if I write it fully in k-space, it would be choosing some normalization. I'm going to already expand the logarithm. So I'm going to assume that this guy is small and expand the logarithm. Trace of G0, J mu, A mu, N. Okay? So I used this thing here, I equated it to this, identified that this is the effective action, and A is 1 minus something small. I expand that something small, and this is the series expansion. So I wrote the effective action as an expansion over A, which is what I wanted. And now I can say that I'll keep the second term, because the second term is the one, the response is the derivative of the action with respect to A, so the second order term is going to govern linear response. And so the second order term is going to look something like, so S effective n equals 2 is going to look something like a half dk. I mean, don't trust the prefactors that much, I guess. Trace G of K minus B halves. Okay, let me write it. That's right. Right here, so S effective n equals 2 is what? Is something that looks like dk d 2 pi over d. Then there's another integral. I trace G0. So this is trace of gk minus pi b halves g of k mu g of k jk b halves mu. And then we have an A nu here with this P, and there's an A mu. Actually, let me write it like this. Okay, I forgot how this goes, but the point is that I expand this, I'll get to second order. The second order, I have this thing squared, right? So I will have two Green's functions, two currents, contracted with two A's, and this is going to be my effective action. And now I have to take the derivative with respect to 1A, or the the variation with respect to 1a. So this is going to kill one of the integrals, and it's going to kill one of the a's. And I'm going to left with this times an a. So this is just the polarization function. So what I did is I calculated this object and derived a form for this guy. So this is the, I'll write it here in a bit more. So this object I'll be using a lot, polarization function. But this is really standard, perturbation theory actually. So here I wrote it, I generalize it to, the current can depend on K, but for my particular theory, the current is independent of K, so I can write it like this. Okay? If you didn't follow this is in every quantum field theory textbook. The point is that this is just a way of writing an expression for this polarization function, which is just Green's function, current, Green's function, current. And it's sometimes written as a diagram. So you have, current here, J, G, and G. K plus B, K plus B. Okay, yeah.
I think I'm missing something. So this is a non-interacting theory.
Yeah, yeah.
So what do we need to do?
We don't need to. We're just calculating this linear response in a non-interacting theory. It's gonna have a surprise at the end, I guess. 5 minutes, great. Yeah, so maybe I'll get to the surprise. Yeah.
So that means that the A field is still not one that's the classic.
Yeah. It's a classic. It's a background. Yeah, it's exactly. Yeah. Okay, so I'm not going to go into the details of how you calculate this object, but basically you plug in this guy here, plug it here, you calculate the traces, and you do the integral. And in fact, you can prove that. Okay, so one thing I have to say is that how does this integral behave? So you see that I have 2 powers of k here, and I'm going to have, so this goes like 1 over k, and this goes like 1 over k. So k squared over k squared. So this integral is logarithmically divergent. So I have to regularize it in some way. I have to either integrate over a cutoff, or another way is doing it in some arbitrary dimension d, and then taking d to be 2, which is called dimensional regularization, dim reg. Or I can do many other things. So the point is that there are many ways of regularizing this object. And no matter what I do, I'll always find this form. I can decompose it into some part that, so note that this depends on P, by the way. So just external momentum. So it's like I'm shining light with a momentum P and seeing what the current is. So I can decompose into a finite part, a part that I don't need to regularize, and a divergent part. And I can write these two guys as finite part is just 1 over pi over b squared, and the okay, let me call it C. So this C parameterizes the results I get when I use different regularizations. And so you see that generically I get an answer that depends on how I regularize the theory. But in fact, this here, it's not a problem because I can impose gauge invariance to get rid of this ambiguity. The way I do it is I realize that I'm calculating this object, J mu, which I know that has to satisfy this because it's charge conservation. So this is just saying that, this thing is 0. So it's just charge conservation. So this means that if I write it in momentum space, it means that if I apply a momentum operator, so this is just the momentum operator, to the current, this has to give 0. But we know that this object is also P, let's see, P A nu. And so this equation, this thing has to be 0 for any value of A. So charge conservation, in fact, implies that this object here, P mu pi mu nu, is 0. So this thing here has to be 0, which sometimes we refer to this condition as the photon being transverse. So you're kind of projecting into P. But okay, so, and now you will see if you just multiply with P here, you will see that there's only one value of C for which this condition actually holds. And this value is C equals 1. So C equals 1 is the only value that I can choose here to preserve gauge invariance, because when I apply P here, I get a P squared, P squareds cancel out, get P nu. I get P nu here, but with a factor of half. So this has to be 1 to exactly cancel the other. So in this case, we can breathe. There's no ambiguity, because we impose charge conservation, and we're fine. So it seems that even though the object that we're calculating was regularization independent, we fixed this ambiguity requiring this symmetry that we know has to hold. However, tomorrow I'll show an example where you impose gauge invariance and the ambiguity still holds. And this is a problem. But in fact, there's a very physical reason of why this is. And this theory actually has that same problem as well. And I think I'll stop here and take any questions. Thanks.